Hi students, and welcome to lecture 13 of the LN 2016A Electronics 1 course. I'm your lecturer Mohammed Dango, and today we'll be looking at an introduction to the bipolar junction transistor. We'll be looking at the construction of the BJT, the regions of operation, different configurations, the schematic, and finally some current relationships. Now students, you can always go and check your textbook, chapter 5, pages 286 to 295 for more information. And please remember that literally everything's examinable in this lecture, so pay attention. So the bipolar junction transistor, there's a very nice little statement in the textbook. The voltage between two terminals controls the current through the third terminal. So looking at our BJT, we have a three-terminal component, and the three terminals that we're looking at is C, which is known as the collector, B, which is known as the base, and E, which is known as the emitter. And here we have a picture of what our transistor looks like. And when we look at the B, C, and E, or base, collector, and emitter, we can see that they are basically PN junctions. And we have two PN junctions in our bipolar junction transistor. And we can configure this in an NPN configuration or a PNP configuration, where in the NPN we have the emitter, which is the N-type, the base, which is a P-type, and the collector, which is an N-type. And similarly with the PNP transistor, the emitter is a P-type, the base is an N-type, and the collector is a P-type. Now, the use of a BJT for analog circuits is usually as an amplifier, and in digital circuits, we usually use it as a switch. Now, when we look on the internet at some of the YouTube channels, they try to model a transistor using two diodes, where they actually say that it's an equivalent diode model of a bipolar junction transistor. Now students, if you do come across this on the internet somewhere, please ignore it. It is bullshit. The operation of two back-to-back diodes is not the same as the operation of a BJT, so please, there is no analogy between them. And we can see that when we take a look at the actual construction of the bipolar junction transistor. So starting at the top, students, we're going to look at the block diagram, which we've already looked at. And one thing to note is the doping and the width of our base. So if we look at the doping, the emitter in either the PNP or the NPN transistor is always heavily doped. And if we look at the base in either the NPN or PNP transistor is lightly doped. And finally, when we look at the collector in either the NPN or PNP transistors, the collector is moderately doped. And we look at the base region, it is a very narrow region when compared to the emitter and the collector regions. Next up, students, we look at the crystal lattice structure, just so we can get a better understanding of what's going on inside of this. And you'll remember these kind of figures from our diode lectures. So looking at our crystal lattice, let's focus on the NPN transistor. So in this N region, which is the emitter, and it's heavily doped, we can see that we've got many majority carriers, which are free electrons. And the green represents our phosphorus dopant, and that is why we have an N-type material here as our emitter. Then when we go to our base, the blue circle represents a boron, and because the majority carrier here is a hole, because it is a P-type material, that's why we dope it with a trivalent atom. And then finally, looking at our N-type in the collector region, we've only got 3 phosphorus atoms here to represent moderately doped, and of course the majority carrier here is going to be the free electrons. Now same thing in the crystal lattice for our PNP, except it's just reversed in that the P region has a majority carriers of holes, the N region here, which is our base, has majority carriers of free electrons, and the collector region, which is also a P region, has majority carriers which are holes. And yes, here we can see from this diagram of the carriers, For the NPN transistor, looking at the emitter region, we have a hell of a lot of electrons because it is heavily doped and it is an N-type semiconductor. And if we look at our base, which is a P-type material, we see there's a hell of a lot of holes. And finally, at the collector, because it's moderately doped, we see that there's quite a few free electrons here. Same thing for the PNP, except we swap around our holes and our free electrons. So take note of this, students. This is an important slide to get to wrap your head around just how the NPN transistor works and the PNP transistor works. And as you can see, it's not the same as having two diodes back to back. So next up, students, we're going to go through the operation of the bipolar junction transistor. And over the next few slides, we're going to see that there are 4 regions in which you can actually operate the BJT. And the first one, looking at this slide, is known as the forward active region, or simply just the active region. And we'll focus on the NPN transistor for this. And basically, in order to operate the BJT in this region, you need to satisfy this following condition, where the collector voltage is greater than the base voltage, and the base voltage is greater than the emitter voltage. Now, when we actually take a look at the circuit diagram to figure out what that means, we see that if our base voltage, which is sitting over here at our base terminal, is greater than the emitter voltage, which sits here at the emitter terminal, we can look at this as being forward biased. So this junction between this N region and this P region is forward biased. Remember, because the voltage at the P region is greater than the voltage at the N region, so we have forward biased the emitter and the base. And if we look at our collector and our base junction, because the voltage at the collector terminal is greater than the voltage at the base, we have reversed biased this PN junction. All right, one more time, students. For the active region NPN transistor, in order to operate it, the condition that needs to be satisfied is we need to forward bias the NP junction between the emitter and the base, and we need to reverse bias the PN junction between the base and the collector. And that will give us an amplifier circuit, which we use mainly in our analog electronics. So moving on, we go on to the next type of operation that we have for our BJT, which is known as the cutoff region. And again, we're focusing on the NPN transistor, and the condition that needs to be satisfied to operate within this region is very simply the base voltage needs to be less than the emitter voltage, and the base voltage needs to be less than the collector voltage. And this would make us have our BJT operate as a switch, which we have seen is normally for our digital type circuits. So let's look at our circuit diagram over here. So in order to operate in the cutoff region, we know that this NP junction between the emitter and the base has to be reverse biased, which means the voltage at the emitter terminal must be greater than the voltage at the base terminal. And of course, at the next PN junction between the base and the collector, we also need to have it reverse biased, so the voltage at the collector terminal needs to be greater than the voltage at the base terminal. So basically, we just reverse bias both of our PN junctions to get us operating in the cutoff region. Thirdly, students, we have what is known as the saturation region of operation. And the condition that needs to be satisfied to operate within this region is simply our base voltage needs to be greater than our emitter voltage, and our base voltage needs to be greater than our collector voltage. And this is also used as a switch, which we know is more for our digital circuits. So let's look at the circuit diagram over here, right? So we need to forward bias this NP junction between the emitter and the base so that the base voltage is greater than the emitter voltage. And again, at this PN junction between the base and the collector, again, we need to forward bias it so that the voltage at the base is greater than the voltage at the collector. So basically, for our saturation region, just forward bias both of the PN junctions. Finally, students, you won't come across this much, but this is the reverse active region for the NPN transistor, and the condition here is the opposite to the active region. So we have to have our base voltage greater than our collector, but less than the emitter voltage. Now the problem with this configuration or region of operation is that it has very poor gain, so we typically tend to avoid it. But just so that we know what it's like, let's take a look at our circuit diagram. So we know that our base voltage needs to be less than the emitter voltage. So we reverse bias this junction between the emitter and the base. And we know that our base voltage needs to be greater than the collector voltage. So we have to forward bias this junction between the base and the collector. Now students, let's take a look at how we can operate the active region for a PNP transistor, just so that you are aware of it. So similarly, here it is the base voltage needs to be greater than the collector voltage, but less than the emitter voltage. And it's used for the same thing as a NPN transistor. When it's used in the active region, it's used as an amplifier. So looking at our circuit diagram, our emitter, which we now can see is a P-type semiconductor material. The emitter voltage needs to be greater than our base voltage, and we see that the notation for the voltage now has become VEB, which means voltage between the emitter and the base. Whereas with our NPN transistor, this voltage notation was VBE, which was base emitter. So we've swapped that around for the PNP transistor. And again, we can see that, all right, we need to forward bias this junction between the emitter and the base for the PNP transistor to be in the active region. So we have a voltage of VE, which is greater than a voltage of VB. And then when we look at our junction between the base and the collector, we know that the base voltage needs to be greater than the collector voltage. So we reverse biasing this junction over here. And of course, that voltage is represented by VCB. Now, finally, students, looking at the circuit diagrams, we have a summary. And I think this is a good point also to take a look at what these actual notations for the different voltages are. So VBB represents the voltage which is between our emitter and our base, and VCC is a voltage which is applied between our collector and our base, for those of you that didn't know. And of course, to summarize for the NPN transistor, we can see the region that we're operating in, the condition that needs to be satisfied, and finally, what is it typically used for when it is in this region of operation. And we have four different ones, which is the active region, cutoff region, which is a switch, saturation region, which is also a switch, and the reverse active region, which we typically avoid because of the poor gain. Now students, it's very similar to derive this for the PNP transistor. So I'd expect you to go and take a look at that for yourself. And of course, in the previous slide, we did look at the active region for the PNP transistor and how we got those equations. And what you're probably thinking now is, okay, sir, but you've got regions of operation. What about the configuration of the circuit? Because we can see you've connected the emitter terminal to the base terminal and the collector terminal to the base terminal. Are there other ways that we can actually configure this component, and what are they possibly called? Well, yes. So, bipolar junction transistor configurations, there are three of them. The first being the common emitter configuration. So here you can see the input and the output have the emitter terminal, which is common. So our base emitter and our collector emitter, that is the common emitter configuration. Next up, we have the common collector configuration, where the collector terminal is common to the base and common to the emitter. So our input here is part of our base terminal and the collector, as well as the output being common with the collector and the emitter. Finally, students, we have the common base configuration. And in the common base configuration, looking at our input and our output, the base terminal is common to them both. At the input, we have the emitter and the base, and at the output, we have the collector and the base. Now, students, we're not going to go into much more detail of the configurations for the BJT in this lecture. Future lectures where we look at the actual biasing and how we go about biasing the BJT will look into this different configurations in more depth. And then students, let's take a look at the schematic for our transistor. And we're looking at both the NPN and the PNP transistors. And I just want to note what the different voltages and current conventions are. So when we look at the schematic, you would have probably have seen this arrow already at the emitter terminal on both the PNP and the NPN transistors. And that basically tells you what type of a transistor you're working with, whether it's NPN or PNP. So if our arrow is pointing down towards our emitter terminal, we know that we are working with an NPN transistor. Whereas if our arrow is pointing up away from our emitter terminal, we are working with a PNP transistor. And that arrow actually represents what is known as the emitter current, which is denoted with IE. So you can see here for the NPN, IE flows down towards the emitter terminal, whereas for the PNP transistor, IE flows up away from the emitter terminal. And if we then follow this emitter current, we go back, we can see that here at this point we have a base current incoming, and we also have a collector current that is incoming. And you'll see in a later slide that if we apply KCL at this point for the NPN transistor, we'll see that this emitter current is simply the base current plus the collector current. And when we look at the terminal between the collector and the emitter, we can have a voltage known as the VCE, or the voltage between the collector and the emitter terminals. Similarly, there is also a voltage between our base and our emitter terminals, which is VBE. Now this also applies to our PNP transistor. So if we follow our current IE from our emitter terminal, it comes up to this point and it splits into our base current and our collector current. So once again, if we apply KCL, IE is equal to IB plus IC. And now when we're looking at the voltages, we no longer go VCE, now we go VEC. And we can see that the positive end should be our emitter terminal. And when we're looking between our base and our emitter, it's now emitter base, and the positive terminal should be our emitter when we're working with a PNP transistor. Right, now students, it's important for us to figure out how the hell this component actually works. And in order to figure that out, I'm going to take you through the active mode of operation for an NPN transistor. So we know that because we're in the active region that our emitter voltage is less than our base voltage, which means we're forward biasing this junction between our base and our emitter. And our collector voltage is greater than our base voltage, so we reverse biasing this junction between our base and our collector. And if we look at the configuration of the circuit, we can see that our VE, or our emitter terminal, is common to our base and to our collector. So this is a common emitter configuration circuit which is operating in the active region, and this is the conditions that need to be satisfied for that. Now looking at the circuit, we have a resistor RC which allows current to flow, RB which will also allow current to flow. We have the voltage VBB, which is the voltage that is applied at our base terminal and our emitter terminal, because that is the common terminal, and our voltage VCC, which is applied at the collector terminal, and of course the emitter terminal, because that is common. And we can see that we have our voltage VCE, which is between VC and VE, or the collector and the emitter terminals. We have our voltage VBE, which is basically the difference between the voltage at our base and our emitter terminal. Finally, students, if we were to look at exactly the base terminal, that voltage is VB. At exactly the collector terminal, that voltage is VC. And exactly at the emitter terminal, that voltage is VE. So now you know exactly what is happening in the circuit. Let's proceed with figuring out how it works. And the first thing that we need to look at is the free carriers and what they are doing when we bias the circuit. And of course, we know that we are going to forward bias this region over here between our base and our emitter. And we're going to reverse bias this region over here, or rather this junction between our collector and our base. Now, when we look at these regions, we know that the emitter region is heavily doped. And because it is an N-type material, the majority carriers are electrons. And there's good reason for why they call this the emitter region or the emitter terminal, and that's because the emitter is responsible for emitting electrons. So the free electrons, which are the majority carriers here, you'll see these are actually emitted from this region, and they will then start moving around the rest of the transistor. Now we look at our base region, which is a p-type material, which is lightly doped. So we know that the majority carriers are holes, but compared to the other two regions, we know that this region's width is quite narrow. And then finally, we look at our collector region, which is also an N-type material. So the majority carriers are free electrons. And of course, our collector is moderately doped when we compare it to our emitter. And the reason why the collector terminal is named the collector terminal is because it collects the free electrons which are emitted from the emitter terminal. So the emitter side will emit electrons. They will travel through the base and they'll eventually be collected by our collector region. All right, so let's actually see how this happens. So starting off, let's look at deriving our emitter current. So when we bias this junction between our base and our emitter, we know that we are forward biasing this junction. So when we forward bias a junction, we know that the majority carriers, which in this case are free electrons from our N-type side, are going to travel across the junction. If you forget how that operates or works, I take you back to lecture 2. Please go and revise that. And because we see these majority carriers crossing over this PN junction, that's going to cause current to flow in the opposite direction. And that's where this current IE, or the emitter current, actually comes from. It comes from these majority carriers moving across the PN junction between the base and the emitter regions. Now, what happens to these free electrons once they move over into our base region? We'll take a look at that in the next slide. But first, we need to note that the equation, or rather the expression, which can be used to determine what this current is, i.e., can be given by expression 2.1. And this expression comes from the fact that there is an exponential relationship between the voltage VBE and the current which is generated due to the movement of these majority carriers. So our emitter current IE can be approximated to IEO multiplied by exponent to the power VBE. So that's how we see it is exponentially related to the voltage VBE divided by our thermal voltage. And this term IEO is simply a multiplying constant, which is usually between 10 to the minus 12 to 10 to the minus 16. And as I mentioned, VT is the thermal voltage. All right, back to our circuit. We said that these free electrons are moving across the PN junction between the emitter and the base region. So they're going to obviously end up in the base region, and then some more stuff is going to happen to it. Let's see what that stuff is. Aha, so here we can see what that stuff is. So these electrons move from the emitter into the base region, and once they're in the base region, there's obviously going to be some holes present in our base region, because we know that the holes are the majority carriers in our base region because it is a p-type semiconductor material. And what happens when we have free electrons and holes? Well, we see some electron-hole recombination taking place. Yes, so that's why you see some of the holes that were available on the previous slide, they've now been covered up because electrons have moved into the base region and they've recombined with these holes. Now, when they recombine with these holes, students, the next thing that happens to these electrons is they start moving out of our base terminal. And they move out of our base terminal all the way to this positive terminal of this biasing VBB. Now, not many of these electrons actually move through this terminal to generate our current IB, because we'll see that a lot of these free electrons actually end up at this next junction between our collector and our base. And the reason why a lot of them do not move out is because of the light doping nature of our base region. So because it is lightly doped, that means there's not many holes available for all the free electrons that are coming from the emitter region into the base region to combine with. So because there's a lack of holes, there's obviously going to be a lot more free electrons that don't have holes to recombine with. And because they don't have holes to recombine with, they end up coming towards this junction between our collector and our base. Right. So yes, some of them recombine with holes and end up going towards the positive terminal of this biasing here, but the most of them end up at this junction between our collector and our base. And of course, we know that our collector region, between our collector region and our base region, we have a reverse biasing that is taking place. But before we see how that works and how it affects these electrons that are now sitting at this junction, we need to note that this current IB that does end up flowing, which is not a lot, because of course there's not many holes to recombine with, well, this can be expressed by an exponent voltage VBE divided by the thermal voltage. So again, it is an exponential expression for our current, relating it to the voltage biasing VBE. Okay, back to our circuit. So all these free electrons are now sitting at our junction between our collector and our base. And we know that our collector and our base junction is reverse biased. So some more stuff is going to happen. Let's see what that stuff is. This should say collector current. But looking at our circuit schematic, we know that this junction over here is reverse biased. So what happens in the reverse bias case is obviously these free electrons are going to move over into our collector region. Now they are the majority carriers, and because they are this is reverse biased, they're going to flow out of our collector terminal. And once they flow out of our collector terminal, they're going to start moving towards the positive terminal of this biasing VCC. So we have all these free electrons at this junction, and because we are reverse biased, they're simply going to move out of our collector terminal and to whatever voltage VCC is applied here. And that movement of electrons, students, is what causes our current to flow, which is current IC, or our collector current. And now we've pretty much derived exactly where the three currents come from, which is IC, IE, and IB. And we can see how it is generated due to the movement of free electrons. And if we were to look at what the expression is for our collector current to relate it to this biasing voltage VBE, well, that's simply our collector current is equal to some factor IS multiplied by exponent VBE divided by our thermal voltage. And we can see that that IS is simply alpha multiplied by IE naught, which is from previous slide, and alpha is known as the common base current gain. And you'll set to know this common base current gain quite well, students, especially when you're trying to spec your transistor. It's very important to know what your alpha value is, and alpha is always less than 1. All right, so now that we've established our currents and we've got some exponential relations between our current and this voltage VBE, we can move on. And here we're going to look at now the common emitter current gain. Now the relationship between the current IC from our collector and our current IB from our base is a linear one and can be represented by this expression 2.5a. And here we have this term beta. And beta is our common emitter current gain. So if we were to rearrange this and do some panel beating, taking the expression from the previous slide for our collector current, we can express our base current simply as our collector current divided by beta, and then we substitute what our collector current is from the previous slide. And note, students, that the beta value often lies between 50 and 300, and it is dimensionless. Next up, students, if we look at our circuit and we perform some good old-fashioned KVL, we can get the expressions 2.7 and 2.8. But wait, before that, let's take a look at expression 2.6, which states that the voltage VBE is equal to VBE on, which is equal to 0.7 volts in most cases. 0.7 volts, that's usually the forward biasing voltage of a PN junction for a silicon diode. And yes, that's exactly what we're looking at here and where that comes from. So because we're forward biasing this junction here between our base and our emitter, this voltage VBE, you will see when you start solving transistor circuits and working with them, this voltage VBE is always VBE on, and that is usually 0.7 volts. Students, don't forget that. That is a very important thing to note when you're solving transistor circuits. And if we were to perform KVL, we can simply get expressions for our collector and our base currents. And of course, from previously, we saw that our collector current is beta multiplied by our base current. And next up, students, it's important for us to derive our current relationships. And I'm sure you remember from the previous slides, the KCL, that I said our emitter current is equal to our base current plus our collector current. Yes, we saw that in our little transistor schematics. So that's going to be our starting point for our current relationships. And we know, once again, this expression has popped up. Our collector current is our base current multiplied by beta. So if we simply take this and put it into our top, we can get an expression for our emitter current, which is simply emitter current is 1 plus beta multiplied by our base current. And then we can find an expression for our collector current, which is simply our collector current is beta divided by 1 plus beta multiplied by our emitter current. Or a better way to express it, students, is to simply say our collector current is alpha multiplied by our emitter current. So now we can see, there's some relationship between alpha and beta. And here is where we see what that is. Alpha is simply beta over 1 plus beta, or beta is simply alpha over 1 minus alpha. And students, that brings us to the final slide of this lecture, which is a summary of the current and voltage relationships for our bipolar junction transistor. This is a very important slide, student, because these are all the expressions and equations that you're going to be using for this component in order to solve the various circuits that you can encounter and to help you understand all the different configurations that we're going to encounter. So thing to note on this, let's start off way here over on the right. For both an NPN or a PNP active mode bipolar junction transistor, we can see these are all the expressions that relate our currents. All right, so these are all the expressions that relate our currents. And of course, we know alpha, common base current gain, beta, common emitter current gain. These will obviously be provided to you in the formula sheet. And now moving over onto this left side, for an NPN transistor in the active mode, these are the expressions for our current and our voltage. And here we see our voltage is VBE because we are forward biasing our base emitter junction. And when we look at our PNP, also in the active mode branch junction transistor, the only difference between these expressions and the NPN transistor is this biasing voltage, which is no longer VBE, it's now VEB instead, because remember, our base is now an N-type semiconductor for PNP, and our emitter is a P-type semiconductor. And so, students, that brings us to the end of our first lecture on bipolar junction transistors. We looked at how they are constructed, and we saw that there are basically two PN junctions in this component. And we know that our emitter is heavily doped, our base is lightly doped, and our collector is moderately doped. We then looked at the regions of operation, and we saw that there were four. And the one that we really looked at in detail in this lecture was the forward active region, or the active region. And then, students, we looked at the configurations. We didn't go into too much detail there. I just introduced the 3 different configurations, which was common emitter, common base, and common collector. We then took a look at the schematic, and I showed you guys that the arrow which points either away or towards the emitter terminal indicates whether you're dealing with an NPN or a PNP transistor. And I showed you that the voltages can also be seen on the schematic, VCE and VBE, or the opposite way around for a PNP transistor. And then finally, students, we looked at where all the different currents come from, and we saw the relationships between all the currents, and we had a bunch of expressions and equations in the previous slide, which will be provided to you, but it's important for you to note exactly where they are coming from. And that's why I took you through in depth how the free electrons move from the different regions, emitter, base, collector, to actually cause those currents to flow. So students, of course, if there's still stuff that you don't understand, I suggest you refer to your textbook, chapter 5, pages 286, 295. And of course, I'd always appreciate any comments, criticism, feedback, whatever you want to call it, for this lecture. Thank you, students. Look forward to the next one.